Hello geometers and seekers of truth. In this video I will explain Euclid's proposition 1-7. Namely this: given two straight lines constructed from the ends of a straight line and meeting at a point. So let's use this picture here. Two straight lines, that's the green one and the blue one for the sake of this demonstration, extending from the ends of a straight line. So the ends of a straight line, that's this particular red line right here, and meeting at a point. So that's, let's call that C up here. So you have two ends here named A, B. You extend two lines up there, A to C, B to C. Okay. There cannot be constructed from the ends of the same straight line on the same side of it two other lines meeting in another point equal to the two former respectively. So that's quite lengthy. So it is worth comparing. So this would be like saying if I have another green line drawn up here and they are the same length, okay, and then I have another blue line drawn from over here extending from B, and the two blue lines are the same thing. This cannot happen. Okay, the second blue line and the second green line cannot meet at a different point. If you were to do that, it would have to meet at point C as well. So Euclid is trying to show that something is not possible, something that cannot happen. Okay, all right, and this is an interesting and fantastic proposition because we can demonstrate this logically. Usually we try to break out some sticks and some rulers and other things, but we can actually demonstrate this logically by using an indirect proof or a proof by contradiction, or in this class, and what Euclid often did, he called it reductio ad absurdum. A reduction to absurdity. Okay, so it starts out this way. The statement says there cannot be constructed. So let's assume, suppose such a construction is possible. Okay. And then we will go and proceed and show why this sort of construction is invalid. So suppose you had a line like this, okay, that made this picture. So let's call this ABC. All right. And then you could somehow extend this to be the same length. In other words, I'm just kind of copying the picture that I have on the left here, but with a little bit more size and detail. Okay, so suppose this was possible. Well, we're going to show that if this was possible, there would be some sort of contradiction, therefore rendering it not possible. Okay. All right, well, let's follow this, the reasoning where it leads us. So what Euclid does is connect D to C. All right? And we can see here that, and I'll write some steps here, since triangle ADC is isosceles, then we can say that angle ADC is the same size, is congruent to angle ACD. Okay? So I will highlight that here. ADC is this one right here, and ACD is this one right there. Okay, this is the base angles theorem, or as Euclid calls it, this is proposition 1-5. If the angles, if the triangle is isosceles, then those base angles have to be equal to each other. Okay? But notice something here, that since, let's get some different colors here. Since if you compare this red angle to this little green one right there, it is clear that the red angle is larger than the small angle. Okay? So in step 3, we can say that angle ADC, that's the red angle, is greater than angle BDC. That's the green one, okay, BDC. And the reason for this is something called a common notion. It's common notion number 5. It says that the whole is greater than the part. Okay, so I'm going to abbreviate here, common notion number 5. The whole is greater than the part. But if you look at now, since the red angle is bigger than the green angle, the other red angle is also bigger than the green angle. So that means angle ACD is greater than angle BDC. Okay. So I've established a statement of inequality, namely that this small red angle here is greater than that green angle there. Now, from the looks of it, it seems that that is impossible. It seems that those two small angles, they're probably congruent, but we can't just simply say by the looks of it. That isn't very mathematical or very logical. So I'm going to erase some of these marks that I have here and just replace them with slightly different marks now. Okay? Because what we're looking for here is eventually a statement of absurdity. Now, if we look at the other isosceles triangle, since triangle BDC, is also isosceles, angle BDC has to be congruent to angle BCD. So there's two blue angles right here. Angle BDC is congruent to angle BCD. Okay? And this is by a similar reason. This is proposition I-5. This is actually common notion 1. Anything that is equal to an equal, they're also equal to each other. So this is saying, that's just the rationale for the previous step. I forgot to write that down. Okay. Now let's keep on going with what we have here. Notice here that, let me change colors one more time. So this little red angle in here, that one right there, that's ACD. It is clearly smaller than the blue angle because it is inside of the blue angle. Okay. So angle ACD is smaller than angle BCD, okay? Because the whole is always greater than its part. This is common notion 5. Okay? Or the other way we can say it is that the part is always less than its whole. Okay? And if you look at here, since BCD and BDC, so since the two blue angles are equal to each other, and one of them is greater than the red one, the other must also be greater than the red one. So the specific names are going to be kind of a mouthful, but if we just pay attention to the picture for a second, the two blue angles are the same size. One of them is larger than the red, so the other must be larger than the red. Okay? So step 7, we can say that since BCD is, since ACD, that's the small one, is smaller than that one blue, ACD is also smaller than the other blue angle over here, which is BDC. Okay. And now if you look carefully, the demonstration is basically done. I'm just going to turn your attention here to two statements here. If we look at statement number 4, ACD is greater than BDC, and statement number 7, ACD is smaller than BDC. So how can an angle be both smaller and greater than another angle? Well, it can't, right? Which is absurd. From step number 4. So therefore, the original assumption must be false. We made an assumption, or we said suppose, right? We pretended like something was true, and that led to a contradiction. But if the assumption led to a contradiction, then the assumption must be wrong. So quaerat demonstratum, thus it has been demonstrated. Okay? So what that means is that this picture is logically impossible. If we were to draw it to scale, there's no way it would work.